Hey everyone, I'm back in my house, in a different room. I think you've seen all of like the major rooms. You've seen all, well, not all. You definitely have not seen all of my wall art. I have a lot. You've seen some of the cool stuff though. This is like my skull and skeleton wall. You see if you can see. It's like pretty extensive. That's not even really doing it justice, but now I screwed up the camera. Okay. No, that's still weird. Okay, no. Oh my god. Okay, that's gonna have to be good enough. Okay. Yeah, and then on the previous ones, you saw some of my. We basically have like themes to the art in our house. We have. Well, we have a two-story house, so there's a lot of room. We got some vaulted ceilings, but yeah, in like the main entryway, like living room, sitting area, we have like this is where I'm at, and so we have like skulls and skeletons on the wall opposite me right now. We have a bunch of landscape stuff. We've done a lot of painting, some stuff like we've gone to painting classes, or some of it we've done at home, me and my boyfriend. Some of it's from just my own stuff, and then we have a whole wall like before you get into the kitchen where it's just this whole hallway of like animal, either we've painted or gifts or stuff that's like animal stuff, and then we have a whole wall that's like dog stuff, and we do a lot of puzzles, and then we frame the puzzles. Not every puzzle, because I think I told you guys this. I'm obsessed with puzzles. I always have a puzzle, at least one puzzle going at all times. Right now I have one in the like our family room, so if we're watching TV, I have one on the coffee table, but I also have one in the dining room. We don't really use our formal dining room a lot, so it's kind of like the space for some of the bigger puzzles, right? And so I've got two puzzles going. And then upstairs we have a whole wall that's like camping, travel, outdoorsy art. And then I have a wall in my bedroom where it's like feminist art and stuff. And then my boyfriend is really into like NASA, so that was one of the walls behind me on the previous video. You can see there was this one little small painting I did where it's like this little spaceman. That was mine. But then when you saw, I think on the video, it showed like some of the other art behind it or above it, and then there was a puzzle, I think, frames. But yeah, I'm obsessed with the walls not having any space on them. We have a lot of art, but I like it because a lot of it, you can see, there's a lot of stuff I've done, or some of these ones like I've done. Yeah, like I did that one. My friend did this one right here. Let's see, I did that one. Like that one I purchased, right? That was a gift from someone. That one was a gift. Oh, there's Alice. Hey, you're on video. She doesn't care. Who's that? Yeah, she's cute. Okay, and then I don't even know if it matters. You can see all my little knick-knackies things I have right over here. So then we got themes. I got a lot of knickknacks, a lot of art. Okay, anyway. It's pertinent to class, right? We got the art, the skull skeleton stuff. Okay, so now that I've wasted 3 minutes, let's talk about, so this should be a short one. So this is early Homo. I say that and I jinxed it. There's only 12 slides on this one, so let's just go through them. First slide. Now remember, so Homo, that is our genus, right? The genus Homo, we are Homo sapiens, right? So all of the species in our genus, like we all share that same genus name, Homo, right? But a lot of species in the genus Homo. And so now I'm going to talk about some of the early ones, more specifically about two, Homo habilis and Homo erectus. And then there's another lecture that'll be later Homo, where we'll talk about like humans, Neanderthals, Heidelbergensis, Floresiensis, like all that. Okay, so if you're following along, see first slide, it says the genus Homo. How can Homo be differentiated from like what we just talked about with like the Australopithecines or the Paranthropines, right? So, because this has been a question in paleo, like, remember, what is a species, what is a genus, and then depending on the lineage, how are we defining this specific genus, or this specific genus, or this other one, or this species, right? What are the criteria for being a member of this genus, or of this order, or, whatever the level is. And so for the genus Homo, along the years, there have been different kind of criteria to be considered, oh, you are now the genus Homo, you're Homo whatever. So it used to be that tool use was the main thing, because a lot of the specimens that were being discovered for what we now would say is something in the genus Homo, they had tools associated with them, like in at the sites, right? So stone tools specifically. And so that used to be a pretty good marker of, oh, this is indicative of higher cognition in some way, innovation, kind of an argument for that a little bit. But as obviously research continued in paleo and anthropology in general, primatology, we realized, well, not even existing now, we're not even the only primates that use tools. Like a lot of the other primates use tools, and some of them are stone tools. So we're like, that can't really be the marker anymore for our genus. So then it's like, well, then what is the marker for our genus, right? So this has been a question for a while. And in fact, in the lecture, I have so if you've taken me in the lecture, you know this, I've had my students read an article called The Human Genus. It's one of my favorite articles ever. And it goes into this exact debate and a few others kind of surrounding, you know, how we name and classify, how we categorize, and like this being a human-made system, you know, are we doing it in the best way that makes sense? What are their criteria? Is there consensus on this? Do we need to rearrange how we're doing some of this? And so in the human lineage, this exact question for the genus Homo has come up. Like, what are the criteria for being considered to be part of our genus, the genus Homo? Like, we've got a bunch of these different species, you know, Homo habilis, Homo erectus, Homo heidelbergensis, Homo neanderthalensis, Homo sapiens, Homo floresiensis, right? So they obviously all have to share something. They're all different because they're different species, but they have to share something to kind of make them all into the same genus. And usually what we say for a genus is like an adaptive niche. They share some kind of adaptation to something. And like I said before, it used to be considered, oh, tool use. But now we realize tool use isn't like the best marker. It doesn't really fit. So what is it now? And so this article, like I said, kind of goes into this debate. And one of the main things being currently that I would say like our field focuses on in terms of what's the criteria for our particular genus, and it is brain size. And so then this calls in, then does everyone who's still considered in the genus Homo right now, would it still kind of make the cut if we're considering brain size to be like the marker, you know, for our lineage? Now, sleepy doggy behind me. So let me just draw a picture. I got some new markers. Let's see, it should be pretty colors. Oh, that is pretty. Okay. So if we're looking at brain size, let me just draw real quick, kind of like a linear, like visual for you to see like some of the brain sizes. So we're talking about the human lineage, right? Now, in terms of the whole lineage, we saw some of the early specimens were at like, I'm going to draw a line, and some of the early ones were at, let me see if I can get, oh, here we go, like 400 cc's, like 500 cc's, right? For some of the like the Australopithecines, Paranthropines, we're seeing their brains get a little bit bigger. You know, maybe we're at like 600, maybe you're approaching that a little bit. But then what we see for the largest hominin brain in our lineage is Neanderthals. So theirs is like 1500. It's really big. Humans were at, let's say, 1400 maybe, approximately. Then we've got like Heidelbergensis at like 1200, and then we've got Erectus at like 1000, right? And then we could just like fill this in like 8, 7, 8, and 9. Okay, so now there's a nice, like, we see a range of different brain sizes in our lineage. There's nothing wrong with that. But let me grab a different color pen. When we're looking at the genus Homo, versus like the others, we could say, oh, Australopithecines are kind of like, this is about where they are, right? In terms of like the brain size. And then if we're looking at the genus Homo, it's like, oh, it's pretty much all right here, except for Homo habilis. Homo habilis is like way over here. So if we're using, you can just see this with a visual, and like the stats back this up. Like, are we saying that as a genus, we're going to include all of these here, clearly very close together in terms of the brain size, and then this other one that's way over here, in fact, much more similar in brain size to this other group, the Australopithecines, right? A lot of differences between them in terms of like their morphology, but in terms of brain size, it's statistically is not even, it's not even like it's an outlier. It's such an outlier that it's not even in the same group, right? In terms of our genus. So if we're using brain size as a marker, we're saying, oh, we're going to pull this random one here to go with the rest of these. It's too big of a stretch, right? And this is what a lot of paleoanthropologists think, like Homo habilis just doesn't really fit in with any of the others in our genus. Like, how we would look at this statistically would be you have to be more similar to each other than to any of the other outgroups, essentially, to be considered like a solid grouping, right? And so it's like these ones are sapiens, Neanderthal, Heidelbergensis, erectus, right? We're all in that like 1,000, 1,200, 14, like statistically we're all similar number. But you've got this outlier, and habilis, such an outlier that maybe not even, like I said, an outlier, is it an outlier? Where's the marker between an outlier and just not even in the group anymore? You know what I mean? That's kind of what we're seeing with Homo habilis. And so a lot of paleoanthropologists have said, maybe we should not include the Homo habilis into our genus. Maybe we should call them Australopithecus habilis. Maybe they should have their own thing, right? And so this is what we say, like this is a human-made system of categorizing and naming and grouping and like what are the criteria that we are making up, right? And now I say making up in terms of using brain size is a perfectly valid criteria, but we are the ones deciding what is criteria and what is not, right? You ask another group of people, they might say, oh, this should be the number one indicator that they're in the group. But someone else will say, oh, this should be the number one indicator, right? So it's all kind of, there's a somewhat of an arbitrariness to it. Now, as a good scientist, we're trying to kind of figure out what's the best way to do this, what markers are we using, what's the criteria, what's the mark for being in or being out, like all of that stuff, right? But this is an ongoing discussion in paleo, so just know that. So it would not be surprising to me if, in 5 years and 10 years or something, if Homo habilis ended up with a whole new a whole new name, either its own particular genus or a genus like Australopithecus or something. So keep that in mind. But when we're looking at these, so still on this one side about the genus Homo, so we're looking at some of the general idea for what we see with the genus Homo versus like previous, genera that we've talked about. Bigger brains is one. So obviously, like primates compared to non-primates, big brains. Our entire lineage, big brains as a group, right? But now we're looking at just our genus within that larger group of our lineage. And even Homo, the genus Homo, much larger brains. So basically what we see, you can see here, is we start out with a little bit of a jump in brain size with the Australopithecines. And then suddenly we get this big jump when we get to our genus where it's like, triple the size, massive. So we don't get big brains until about, 2/3 into what the lineage is right now. And so those preconceived notions people had before, that big brains were going to happen at the beginning, like, if we're looking at in terms of, the lineage with like humans, see if I can draw that upside down, like humans, chimps, and our last common ancestor, it's like a little bit, it's like a little bit bigger, a little bit bigger, a little bit bigger, a tiny bit bigger, and then boom, like massive jump in brain size, right? So much later in the lineage. General trend of slightly rounder heads. Now there's no goal towards having a round head, right? We just see that happening a little bit. We see more of a forehead because we're getting more of a brain up on top rather than just all behind, because the brains are getting bigger kind of in all directions. And depending on the species within the genus Homo, there's going to be some differences in that. In general, faces are getting kind of smaller, mouths are getting smaller, right? And just for clarity, there's no crusting or anything like that in our genus, no surprise, right? And reduction in prognathism, so primates compared to non-primates, flatter faces, right? Hominins compared to other primates, flatter faces. But our genus, the genus Homo, compared to the other hominins, even like flatter faces, right? Very flat faces. Moving on to the next slide. Oh, just another one of those timelines to kind of show where we've talked about the early genera, the middle group of Australopithecines and Paranthropines, and now we're moving into our genus, the genus Homo. So you'll see on the next slide an image of a skull, and this is a Homo erectus skull. And you'll see here the two early Homo species that I'm going to talk about for this particular PowerPoint are Homo habilis and Homo erectus. Homo erectus, you'll see here on the image, you can see the brain is pretty big. And Homo erectus on average has a brain size of about 1,000 cc's. But you can see here it's what we call like a football-shaped cranium, or like a long and low. It's pretty big, but a lot of it's kind of big behind, right? Not necessarily up here. Now, there's no goal towards having your brain more up here than here, but we just end up seeing some differences, like with erectus and let's say like Neanderthal, a lot of their brain, even though it gets bigger, kind of gets bigger behind, versus in Homo sapien, we see kind of getting bigger up here. The general consensus is that this has to do with like which lobes are more or less developed, depending on the species, right? So the shape of the head, the brain and the head might change. Next slide. In fact, okay, I'll talk about this. So the next two slides go into this little bit of a debate. It's not really a debate anymore in paleo, but it used to be. Essentially, like I mentioned before, there's a time when there are no fossils and people are just unearthing fossils and trying to figure out what they're looking at. Am I looking at one species or another? Is this a species with a lot of variation? Because even like we look at modern Homo sapiens skulls, if you didn't know when you saw different skulls from different ancestries, you might think, wow, there's a big difference in what they look like. Is this enough of a difference to say they're different species? But then because we know humans, we can observe humans as a species like in real life with soft tissue and all of that, all the social stuff. We're like, oh, one species, right? Enough interbreeding between all the groups ancestrally, one species, just different because of some ancestral things, right? But for a lot of other species, when you don't have soft tissue, when you can't observe them in real life, it's harder to tell. So like, let's say you've never seen a gorilla before, but you had a male gorilla skull and a female gorilla skull. If you didn't know anything about them, you might think, oh, I'm looking at two different species because their skulls are massively different, right? We've seen this in the lab, like the male gorilla skull, massive amount of cresting. It's like, it's like 60-70% larger. All the features are more prominent. And if you didn't know that it was a species that just happened to have a lot of sexual dimorphism, you just had one skull and another skull, and you were like, what is this? You might think, oh, I'm looking at two different species, right? So this is one of those questions, kind of this debate early on in paleo, where there was two specimens found, similar location, same dating, and there was this question of, okay, are we looking at one species that is sexually dimorphic, because one's kind of bigger than the other, or are we actually looking at two different species and they just happen to live around the same time, the same location, which is possible. Like both, if you didn't know anything else, all you had were two skulls in front of you, and you saw one was small and one was big, and some of the facial features were, of course, different. That would be a question in your mind: am I looking at two different species, or am I looking at one species? But it's just dimorphism, right? And so, but then of course, as we do in science, more evidence, more specimens, more, data collection, et cetera, and you can see on this slide, and you go to the next slide, you'll see kind of the top-down view of these two skulls, and basically, there's some fancy words there, like the specimen number, you don't need to know that, but essentially now we would say, oh, these are two species. One is we've named Homo habilis, one we have named Homo rudolfensis. And even with just these kind of grainy photos, I hope there's something that kind of pops out to you in them, in that even though one is bigger and one is smaller, which there's a little more to dimorphism than that, but that's kind of an interesting place to start, you might think, well, how could they tell that it's not just one species that's just sexually dimorphic? And if you look, like I said, even in this grainy photo, you should be able to tell that the smaller one has all of the more robust features to it. The bigger brow ridge, like you can even see some of these things popping out, right? And what we know about how dimorphism works in like mammals, right, is that the male is always the larger one. Now in things like marine life or insects, it can be trickier, right? But when we're talking about like primates or mammals, it's the male that is going to be bigger, larger, And so if we see more robust in the bony features, when we see two specimens right here and the smaller one has the more robust features, we know that's not dimorphism at play. We know it's probably just two different species, and that's what we have decided now as paleoanthropologists. So just know there was kind of this interesting thing. But even as interest students, you should be able to kind of think of some of that conceptually and say, oh yeah, it makes sense that they're not the same species with dimorphism, because the one that has all of the more masculine or more robust traits is the smaller of the two, and that's just not how sexual dimorphism works in primates or mammals. So moving on to the slide that says Homo habilis. So now moving into one of the two species I want to talk about, Homo habilis. So some features you'll see, some bullet points. Brain size, like I said, we have a pretty decent brain size. It's definitely bigger from what we saw before. It's moving up. So it's increasing in early age. We see that nice parabolic dental arch, a nice arch, to the dental arch. It's not parallel tooth rows, so basically our faces are getting a little smaller and accommodating that dentition. We're seeing more of a forehead and a little bit more of a brain up here. Like I mentioned, not that there's a goal towards having a brain more up here than behind. It's just we see it in some species, we see it in other, it's a little bit more in the back, etc. So like I even have here, small brain but larger than the Australopithecine. So okay, there's that. And then that question, which I already addressed, should Homo habilis be included in the genus Homo? And I've already talked about that, right? So that's kind of food for thought. You can see on the timeline where we're kind of at, and like I mentioned on the previous one, Homo habilis existing around the same time as the Paranthropus, the genus Paranthropus. And so I think there's evidence that we have that they interacted to some degree. It's assumed that this probably happened. Now we don't know the details. We may never know. Just like even with Homo sapiens and Neanderthals, we don't really know exactly. We know there was interbreeding going on, but to what extent, what the scenarios look like, we don't really know, right? And what I forgot to mention, I forgot to put a bullet point here for Homo habilis was, because in this class in the lab we're doing a brief overview and we're talking about most of the morphology, but just kind of as a reminder of what you talked about in the lecture, or at least you should have, we see the stone tools in association with Homo habilis, which I already mentioned, and so this is where kind of the name Homo habilis comes from. It's like handyman, essentially. So we're seeing tools, and also look at this really cool Smithsonian recreation. If I said, hey, that's something in our lineage, actually fairly recent in time, you would think, oh, I could kind of see that. Okay, moving on. The next one, Homo erectus. So now you'll see we are at 1.8 million years ago. Now recall, I said for the other species, you don't need to remember the exact dates and locations. However, you need to remember that general timeline of like, okay, this one was first, this one was next, like that kind of thing. So we were talking before about 6 million years ago, 4 million years ago. Now we're only talking about less than 2 million years ago, so much more recent in time. And you'll see here it says on that second bullet point, East Africa, then out of Africa. Homo erectus, as far as the evidence points to right now, Homo erectus is the first hominin to leave Africa. Some of the population stayed in Africa, some went into modern day Europe, some went across the continents into parts of Asia, and as far as that evidence that they're the first ones of our lineage to do that. I think there was a paper in the last couple of years, there was evidence that possibly Homo habilis exited Africa to a certain extent, but I'd have to look into that again and see if anything came of that. But like I said, as far as we know, erectus is just spread across the old world, essentially. The first erectus specimen was discovered by someone named Eugene Dubois, and kind of similar to that story I told you about Raymond Dart, Eugene Dubois, he thought that, because a lot of the scientists at the time were like, okay, humans are obviously related to the other apes, right? They knew we're like chimps, gorillas, orangutans, whatever. Like, we're all clearly related in some way. But which one are we maybe more closely related to than the others? Eugene Dubois thought we were more closely related to the Asian apes, orangutans and gibbons. Now, he ended up being incorrect in that, but we do have some of our ancestry in Asia, and that's where he ended up going. He was hoping to find ancestral fossils of our lineage in Asia, which he did. He found the very first Homo erectus skull, but kind of similar to Dart, a lot of his stuff was disregarded. Oh, that's in Asia. Oh, you probably just have a ancestral gibbon. And he's like, it's not a gibbon. it's something in the human lineage, right? There's a crazy story about Eugene Dubois. He and his family, they basically went on a couple different expeditions, but they were there with the Dutch army, and everyone got malaria, and he was there with his wife and his infant daughter, I think. And I don't know if I have this on a slide. In the lecture I go into it a lot more, but they got abandoned there, and some of the people stole their supplies, but they made it out. They lived. It was just this crazy story. I'm sure there's a documentary about it. It's crazy. Here I have listed some of the sites, in, let's see, in different parts of the world, like Asia, Africa, where erectus is really just everywhere. And now look at that Smithsonian recreation, right? No surprise, as we get more and more close to modern Homo sapien, we're going to see things looking more similar to us. Not that there's a goal towards looking like us, but obviously we know that's what happens for at least part of our lineage. And so it's interesting to see how the similarities and differences kind of occur through time. The next slide, some characterizing features of Homo erectus. Now, like I mentioned, every species has interesting and unique things about them. Obviously, that's why they're their own species. However, we can kind of point out when some of them, at least for the intro course, are a lot more easy to kind of see and stuff. And so Homo erectus has some really unique features. The first is that they have very thick cortical bone. Now, I think we talked briefly about cortical bone, but let me just draw you. I think we talked about cortical bone briefly in like the skeleton. I think I drew a picture then too. If you missed that one, I'll draw another. Oh, in fact, yeah, I was looking about how many views I've been getting on some of these videos. It seems as if most of you, like for the early part of this, I mean, I know it's a fast-paced course, but it seems as if a lot of people were watching the early videos and then not as much watching on the later videos. So I get it. I mean, I do, but just, no, obviously I'm giving you a lot of information right now that in class I'm only talking about for 1 or 2 minutes or something, maybe if someone asks me. So if on the exam or something, a question comes up that I've talked about, I'm assuming everyone's watching these when I make them, but obviously I know that's not quite happening. So I get that maybe you miss 1 or 2 or something. There's a lot. It's all crammed into 4 weeks. I totally get it. But just, try to make the effort when you can to do that. Okay, so what was I going to draw? Oh, cortical bone. So first I'm going to draw a femur. Poorly. Let's see. God. That's... I feel like that's such a... Hold on, let me just adjust that slightly. That's so much worse. It's okay. Okay, that's a horrible drawing of a femur. You guys get the picture, right? So it doesn't matter. Just imagine there's a bone, right? Now imagine I took this bone and I cut it right there. I cut it on that plane. And then I take the shaft and I rotate it towards you. You're going to see like a cross section that looks something kind of like that, right? Well, I'll make this a little bigger. So on the cross section, let's say for Homo sapien, there's 2 types of bone, cortical and trabecular. Or you could say, cortical is this like this dense outer bone. Let me see. We could say it's either cortical or compact bone. So we can fill in, it's like dense and thick. So think of like, I'll do it the whole way, but think of like, a really good example of this is like cardboard. You take like a piece of cardboard, you're looking at, the inner workings of like one of the flaps or something. You can see on the outside it's thick and dense and durable, but the inner workings, it's kind of more porous. And this is exactly what we see in the bone. So let's say on a Homo sapien, we're looking at, the thick outer bone, and then internally, it's more porous. And we could call this bone either trabecular bone or cancellous bone. If you ever hear the term spongy bone, this is absolutely incorrect. I don't know why some of the lab books or some instructors continue to use this word, but it is wrong. It is a misnomer. The bone is not spongy. For intro students, they get confused by this. It is not absorbent. Do not use this word. If you see someone else using this, you can call them out. It is completely wrong. I don't know why I keep hearing this or seeing this. It's not spongy. It's totally the wrong word. It's porous. It's still bone. It's hard. It's bone, but it is porous, right? So spongy, I swear if I hear you say spongy bone in class, I'm not going to do anything, but I'm going to correct you. I'm going to correct you, right? It is absolutely wrong. I would say if you take, 5 things away from this course, let that be on that list. Do not use spongy bone. Anyway, but so here we have, the cortical bone on the outside, cortical or compact bone, and the inside, the trabecular or cancellous bone. Now, this is on a regular, like say Homo sapien. In Homo erectus, this outer cortical bone is very thick. So imagine, like more like that, like just massively thick. Like twice as thick as what we see like with us or any of the others. So it's very, very thick. Now what this tells us is, because the whole idea of us having cortical compact bone that's thick and dense on the outside, but more porous in the middle, is it allows it to be durable but lightweight. And so when you see in an animal, here in the case of Homo erectus, that the outer dense part is really thick, Usually the body won't do this because it can cause a problem with like the amount of weight, that you're carrying around in the bones. But obviously natural selection selecting for something like this because it was needed. Essentially what's going on with Homo erectus is they have a much more physically demanding life, what we see. And some of these other features here that are on the bullet point are kind of going along with this whole idea of that they were living a much more physically demanding life. And so you see some of these other features, right? So we have what's called the sagittal keel. So on this area right here, remember, on Paranthropus, it was a sagittal crest, specific for muscle attachment. In Homo erectus, it's not the same thing. It's in the same location along that sagittal plane. So similar name, but it's a sagittal keel. And you'll see it on this image on this slide. It's a little tiny bump. Instead of it being a big bony mohawk, it's kind of this little bump like right here. It kind of runs most of the way on the head. This is basically a little bit of extra bone for shock absorption as this bone or this individual is getting maybe hit by stuff or moving around a lot more and being more physically demanding. Basically, a lot of these features on the skull are for extra shock absorption. So you'll see here, even in the back, a nuchal torus. So this feature on the back of the head, basically a few extra layers of bone for shock absorption. Even on the brow ridge, it's not functional for anything. The brow ridge isn't there for like muscles to attach for chewing or anything. It's either, sexual selection, maybe part of it, but also for this whole system of shock absorption. If you're constantly getting knocked around in the face, the head, the body, having extra bone in the right place, shock absorption for some of that is going to be beneficial, right? So moving on to the next slide, you will see one of the very famous specimens for Homo erectus called Turkana boy or Nariokotomi boy, and you'll see here 80% complete. So remember, Lucy was 40%, which really meant like we had like 80%. So having an 80% basically means we have essentially the whole thing. Now there are a few things missing, like you can see some of the hand bones are minimal, but this is basically a complete skeleton. It's an amazing find. And also what we know is that this individual was a juvenile, so once again, having a juvenile is very important. And I think they estimated that in adulthood he would have been like 5'8" or something like that. I'd have to look at the exact number again, but like completely within modern range of height. So now we've got, biped, tall, and then we see this jump in brain size. The next slide goes into the tool type difference. So we found tools in association with Homo habilis. We also found tools in association with Homo erectus, and we've given them names, The stone tools that are found in association with Homo habilis, we have given them the name Oldowan tools, and the tools we found in association with Homo erectus, we've named the Acheulean tools, right? And a big difference between these tools is very important. So Homo habilis, their tool, basically imagine you have two rocks and you're pounding them into each other. You're going to try to get maybe a couple sharp pieces to flake off, or maybe get a sharp edge on one of the rocks so you can hold the rock with the smooth edge, and you've got a sharp edge here on the other side so where you can cut into something, right? A simple tool, but Homo habilis needed a simple tool for a simple task. Totally fine. Acheulean tools, though, for Homo erectus, basically a more complex tool. You can see here what we call bifacially work. So they're taking a stone and they're taking the time to shape this. So instead of it taking like an Oldowan tool where you're smashing them, maybe taking a few minutes, 20 minutes, 30 minutes, maybe an hour, now you're seeing with the Acheulean tools, hours and hours of creating these complex tools. There's also a lot of debate about what these tools were used for, but like that's kind of a topic for another class, right? But just so you know, these general tool types, more simple, more complex. And so be careful though, this does not mean that Homo habilis could not have made a more complex tool. They probably could have, right? But there's a phrase called necessity is the mother of invention. Basically, you're not going to just create a more complex tool if you don't need it, right? There's going to be a need for something, and you're going to create a tool or a weapon or whatever to accommodate that need. And so could Homo habilis have made a complex tool? Probably, but they had the brain size for it, right? But they didn't really need to. They had a simple thing they needed to do, and it worked for them for a long time. Very successful at it, and then environments change, and then we see tool types changing. The main difference, what we see going on, reason why we see this change, and if we go to the last slide of this PowerPoint, you will see this has to do with the transition in diet. Now, up until this point in our lineage, all plants, right? We're eating plants, different types of plants, but we're all plant eaters at this point. It isn't until Homo erectus that this change, well, Homo habilis and erectus that this changes, right? So what we see with Homo habilis, kind of this transition between habilis to erectus, is this transition in the type of, like I said, the diet and how we're getting the food. So all eating plants at this point, but then and you can kind of see this on the PowerPoint slide, there's this transition between passive scavenger, active scavenger, and then hunter. Passive scavenger is, you're walking around and you come across a carcass, right? And maybe you utilize what's left, right? But if you come across a carcass that's been there for a couple days or something, and whatever animal took it down, it's got all the good parts, right? So what's left? The bones, right? Maybe you're lucky and there's a little bit of, maybe some fat or muscle, but probably not, right? It's going to be mostly just the bones. That's it. Now, bones can still be really useful, even for the diet. There's something inside the bone that we see is starting to be eaten, right? Think about for a second, what that would be. It's marrow, bone marrow. So now we have a whole new thing introduced to the diet, right? We've got marrow. Oops, that pen's not working, of course. We've got bone marrow. A whole new thing introduced to the diet. So the Homo habilis were using this very simple tool with a little bit of a sharp edge to break open the bones. Simple task, simple tool, nothing wrong with that. They did it for a long time, we're perfectly fine. And now we've got an introduction of a whole new dietary item. There's something that marrow has that plants have, but typically not in really high amounts. You think about it for a second. Fat. Now we're getting an introduction to some more fat into our diet. And then, like I said, we're seeing this transition from passive scavenging, active scavenging, into hunting from habilis to erectus. So active scavenging is you are waiting for a predator to take down the animal, but you have a way of getting that predator to leave. So remember, passive scavenging is you come across a carcass, it's basically bones left, that's what you get. Active scavenging is you're like, I'm gonna let the lion take down that deer, but then I'm gonna use fire, for example, or something, weapons, to get that lion to go away, and now I can get 80-90% of that carcass, and I'm getting access to a lot more, right? And then of course hunting would be you're doing it all. You have strategies, for taking down the animal, catching it, processing it, the whole thing, right? So we see that transition from habilis to erectus. And so what we end up having is, while we're still eating mostly plants, here's the thing, and this is very important, and like I said, if you take only a few things away from this class, this is probably a really, really important lesson. Basically what's on this slide is really important, because you'll hear this, and it's almost always incorrectly used. We have big brains because we're meat eaters. That is false. I'll tell you right now, that's totally wrong. Think about all of the animals that eat purely meat. Would we say they're they have all these really big brains, or highly intelligent? Now, of course, we know every animal is intelligent in their own way, and a lot of carnivores are obviously very smart. But when we think about humans and we think, we're the smartest, we have the biggest brains, or whatever we say, right? And it's because we're meat eaters, it's completely false. It's unrelated, right? Think about the animals that eat purely meat. We're not carnivores, right? If anything, we're omnivores, and that's very recent in time. In the last, less than 2 million years. Considering our entire lineage is plants for millions and millions and millions and millions and millions of years, right? So, but when people say that, it's not fully incorrect, because there is a relationship. And here's basically what's going on. So, like I said, we've got marrow and fat, and then obviously muscle is being introduced to the diet. So now we've got some muscle, which of course, adds more protein. I don't know if you guys are aware. Plants, especially dark greens. Did I spell protein right? Why does that look weird? Oh, that's right. Dark greens have a lot of protein. Now, you can be a vegan, vegetarian in 2025 without any issue, right? You can go to the local Smiths and get food from all around the world, different seasons, a wide range of foods where you can get everything you would need, protein, fat, whatever, right, on a strictly plant diet. In the past, though, obviously, you only had available to you what was in your environment, so a totally whole different story, right? And so you could have a decent amount of nutrients in your diet from plants, but like I said, probably low in fat, which pros and cons to that, right? Protein, you're getting a decent amount if you're in an area where you're getting darker greens and stuff. But obviously adding in the animal is going to add to that amount of protein. And then, like I said, we're still eating mostly plants. So we've got plants. Now there is something that is vital to having big brains. Brains take up our big brains take up 25% of our body's caloric energy. That one organ, 25%. It's insane. There is one thing that we need to power that organ what we get from plants. It's one thing that's very important. We have to have a lot of it. It starts with a G. I'll give you guys a second to guess, or pause it and guess, right? It's glucose. We have to have a large amount of glucose to have a big brain. And when you think about most of the animals, we think of like as being like smarter and stuff. A lot of them are like omnivores or plant eaters, right? So anyway, but for our lineage, big brains, we have to have a lot of glucose in our diet to power our big brain. Now you might be thinking, well, I've heard this thing about like meat eating and that's when we got big brains. They do coincide with each other, like I said, but it's not because of the protein. That's totally incorrect. That's not it at all. In fact, like I said, we could have protein, whatever. We need glucose to power our big brain. That's what we need. That's what powers our big brain. The reason why we see that connection is because what's going on socially, and it comes down to one thing. Complex communication. We need bigger brains, higher EQ to be able to do this, right? To have a higher cognitive ability to be able to communicate with each other. When you go from a system of, hey, I'm walking along with my buddy and we find, a carcass on the ground and we use it, to now we have a whole strategy, tools, weapons, for the whole process. Now we have to have a strategy of you go here, here's what we're going to do. You're planning it, right? Massive cognitive difference between, we happenstance found something on the ground, to creating these whole elaborate strategies for hunting, which means you have to have the ability to communicate with each other, which is why we're pretty sure as paleoanthropologists that Homo erectus is where we see the first, probably early forms of language, right? We have the first forms of fire too. We see evidence of that with Homo erectus. And so no surprise. So it's not the protein that's giving us our big brains. That's unrelated. We need a lot of glucose to power our big brains. It's the complex communication that's driving it, which is we're using it to get other things in our diet, right? So they're coming up with all these elaborate strategies and ways to get these animals. You have to be able to communicate with each other. So there's this natural selection. There's a selection on those who can communicate better, those who have a larger brain, higher cognition, in those ways that it's related, like we talked about before, with like EQ and all that. So it's not what they're getting at the end of it. Like, that's just whatever. It could have been anything. It could have been they have elaborate strategies to get water. Like, we just happen to see that in this case it's animals, and it happens to be muscle that they're getting. They probably cook it. They're cooking it, right? They find it tasty, whatever. It could have been anything. It's what's going on here that's the most important part. It's the complex communication that's driving that. That's why we have the big brains, and the fact that the majority of our diet, like 70-80% of it, was still plants. So when people say, meat eating gave us our big brains, like, it's wrong. It's so wrong. Like I said, it's not unrelated, because there's a strategy, the hunting strategy, and the complex communication is what's doing it. So keep that in mind. And like I said, nowadays, you can, because we have such, globalized world, you have access to all of this food. You could just, go into the store and get everything you need from a plant-based diet. It's like not a problem anymore, right? So keep that in mind. Like I said, if you take only a few things away, this should be one of that complex communication. I just see I have a typo in that PowerPoint slide. It says complex, but whatever. Okay, guys, a bit longer than I say, jinxed it, right? A bit longer than I thought. That's fine. I kind of went off a little bit on a few things in more detail, which is totally fine. And I'll see you guys on the next one.